Alright, here is a video for homework 4, the solution to homework 4 in ME370. The problem, it's kind of like this backwards thing, right? So we have a strain gauge and we want to figure out what the loads are that are going to be on the end of this pipe. And we're given this strain gauge data for strain gauges 1, 2, and 3. And you can see how they're aligned with the X and Z right here. And we know that the pipe is a 2.5 inch diameter, schedule 10, and I gave you the outside diameter and the wall thickness. It's made out of stainless steel, and I gave you the material properties, and the dimensions are 36 inches here and 24 inches there. We want to find the internal pressure and find what the forces are applied onto the end right here. So here we go. I wrote down my little sketch of the thing. I try to be kind of extra neat with it. I actually used some of my isometric circles templates. I hadn't used those in a while, so I actually got out the little templates and made the little isometric circles correctly. Alright, so here's the information that we've been provided right there, and there's what we want to try to get out of this. So the first thing I want to do is I want to transform these things into I want to try to figure out what the X strain is, the Z strain, and then the gamma XZ right there. So I take a look at the angles, and I decided that this one right here was going to be 30 degrees, right? And that this one was going to be 330 degrees, and this one was 90 degrees, all with respect to the x-axis right there. So there's where I decided to do, and here's our strain transformation. So here's the first equation that I want to plug in, and I go ahead and stick in the known value here. I'm going to keep them as micro strain just for the time being, so I don't have to write out a bunch of decimal places and stuff. And put all the 30s in there, and we end up with this equation. Right, so here's our 3 unknowns right now. So I do it again now for the second one. So making sure that this 2 and that 2 and that 2 and that 2, these are all, the angles correspond with the strain that we've gotten from the gauge. And we stick in the angles, and now we have a second equation. And there's 2 equations and 3 unknowns. So we go to the third one here, and now this is going to be the 90, and this was going to be a little easier. You can see that some of these cross out right here, and this one turns into 1. So we can say that EZ, or not EZ, epsilon Z, is equal to this right here. It just ends up being equal to epsilon 3. But it kind of makes sense from the original one because this is aligned with the z-axis. So we're good to go there. Alright, so now we have, we're able to replace that into equation, the equation 1 that I had up above, and come up with, I'll call this equation 3 with 2 unknowns. And then we do the same thing here for, we did have equation 2, what we had before, and we plug it in. And now we have 2 equations and 2 unknowns. And so we can solve for epsilon x and gamma xz. So just a little bit of algebra going on there until we can find my gamma xz is going to be this in microradians. Now, and then I think I overlooked to write out that I also found, I plugged it back in, plugged it in as microradians back into one of the other 2 equations, either equation 3 or 4, and I'm able to get 14 microstrains is what this ends up equaling. Okay, so now what I want to do is I want to get those strains and I want to turn them into stresses. So we call them the constitutive equations, right? They're just a little bit more complicated than just taking Young's modulus, but it's a combination of Young's modulus and Poisson's ratio. So here we go, and these are the backwards ones, and this is in the case for biaxial strain, right? So I have I've given out this equation for that, and so you can see plugging these back into there, we end up with getting predicting that the stress in the x direction is going to be 41,759 psi. You can do the same thing for the z direction here, and we get 7,188. Right. So these are the normal stresses that are on this at this location. I need to get the modulus of rigidity from the material properties that were given. So, and with that, we can directly get the shear stress. It's just multiply modulus of rigidity times the shear strain. And then I'm going to do some geometry stuff. Figure out what the inside radius. Remember that it's going to be 2 times the thickness when you subtract from the outside radius, and might as well get the inside. I said radius, I'm a diameter. Here's the radius, right? Just 1/2 of that. And here's a good thing to check, right? For your pressure vessels, we see that it's less than 0.1, so we could use the thin walled. Save us a little bit. There's the area, the cross-sectional area of the pipe. And here's the moment of inertia. Make sure that you're putting the 4 onto the individual diameters here and not sticking it out there. That's a common mistake. And it's still symmetric, axially symmetric. So just take 2 times I to get the polar moment of inertia. Now we can start with stress. I'll go working backwards from stress. Actually, we already have the stresses. So I summarize them on a stress element. It's always a good idea, right? And notice that's the x-axis and the z-axis right there. And we can figure out from the hoop stress, and once again, we're using the thin-walled equations here, and that's aligned with the z, right? If you look back at the original problem, you can see that hoop works to try to, just like you're inside the hula hoop and you're trying to expand it, and so it comes out with a tangential, and that ends up being in the z direction in this orientation for this problem. And we're able to find out what the pressure is in psi. And then we, because we have the pressure in psi, we can find out what the longitudinal stress is, and we know that's going to be in tension. Maybe I should have written tension right there. No, not tension. That's stupid. We already knew that it was in tension. No, that is. No, that's fine. I don't know. I can't put tension in there. I don't know what I'm thinking. I was thinking that was a pressure all of a sudden. But no, that is tension. Yeah. Okay, it was fine. We also have the gamma. Well, we also have tau, and maybe this should have been like xz, right? Could say there was xz. And we know there's no transverse shear at this location, right? Or are we just assuming that? Wait a second, let me take a look at this. Yeah, we have no transverse shear because there's no force coming in this direction, right? So that would be the force in the z direction would cause transverse shear onto this, but we don't have a force. So all of the shear is from torsion, right? So we're able to find what the torque is. And since we know the torque, we'll make a little free body diagram here and figure out the relationship between this Fy, unknown Fy. Now, one thing is we don't really quite know whether the torque is going positive or negative. I didn't bother to try to establish which way it was going to go based on this. Based on the strains. I would have said that it was going up in this way right there. But I think we could later on figure out that it has to be downwards in order to cause tension in bending, right? So I assume that the direction is downwards. We'll find out in a second because we have tension for bending. All right, so we get to, the next thing I want to do is I want to find out that bending. So here we go. Here is, with that new force we just calculated that we got because we knew the torque, we're able to get what the moment is. And that's the moment, if this thing is going down, it's coming this way, and it's going to cause tension at the top where we want it to be. So using the tensile stress, using the moment, we find we have this, and this is in tension, so we should probably put that on there. And we can say that we know that in the x direction for stress, we're going to have a combination of bending, longitudinal, and axial, right? So we can see that longitudinal is pulling this way, bending is pulling this way, and axial is going to pull that way. But we'll see when we get to, we can find the axial by subtracting out from the x, the bending, and the longitudinal, and we see we get a negative number. Therefore, it must be in compression. So for the axial force that we have right there, we just have to multiply that axial stress times the area, and we get what that force is in compression. So there are the answers for that problem. And there's a chance I made some mistakes along the way. It's really, I like this problem, as I've said before. I like these kinds of problems because they're very much like a practical, real-world thing, like to try to actually figure out the forces from strain gauges that you can actually measure. All right, so let's see. We'll talk about the next problem. And the next problem was a curved beam. Let's take a look at the original problem here. I went and I did some searching online, and I found a manufacturer of very large hooks for cranes, and this is actually a real company. You could go to this website here, and I'll allow it. I'm a little afraid now not to allow it. I don't know what we're going to go to, but if you go to this crane hook manufacturing company, there it is. There's the big hook, and here are some of the dimensions and stuff. I decided to go with the 100-ton. Just want to see what kind of stresses are we going to get on this 100-ton. So I included that little figure here in your homework right there, so you could see that these different parameters. But we're going to assume this is like a trapezoid, right? It's an okay assumption. It's not. It's decent. At least we have the information in the book, right? So I said we have this B, and B1 is, and then we have H right there. So you can see that I have B, B1, and H to define this. And I also note that they gave us a radius right here of curvature of for the outside. So this is like RO. But note that the force is actually in line with this point, so there's an offset of that little baby I right there. So I included there. So there's here's what the values are, and then I took 100 tons and I turned it into kilonewtons for you there. So we'll go back onto this, and I drew out. I didn't do a great job of this. I shouldn't freehand it, right? But anyway, so one of the very first things we'll do in a lot of these problems is to try to figure out how the variables match up, right? So we have Ri. We can find that by taking the height, where I think I'm subtracting the height, right? Yeah, right there. I'm subtracting the height from this O that they gave me. So that'll give me this inside radius right here. And H is actually equal to H in this case. That was nice of them. BI, what we usually use for BI, is actually going to be that capital B, right? So that's the inside width, that's what they're calling it for B. And then for BO is just going to be this B1 that they gave right there. And then lastly, the RO, I should have started with that one probably, as equal to their O. Now we want to go for and find the radius of the centroid. Now, do I have, here's the big question, do I have the book open? No. So going to the curved beams, where'd you go, curved beams? Why aren't I seeing you? Shear stress, torsion beams, curved beams, there we go. Curved beams, we go to this table, and we look at this. So we're going to put all the inputs that we know in for this RC and this RN. We also want to get the area when we get to that. So here is me putting into the this equation. All right, so the RI, I'm seeing that in there, and H we know, and BI and to BO, we have those. And I kept it as millimeters just to I'll turn it back in when into meters when it gets time to actually use it. One thing to know that I used extra sig figs here because we're about to subtract two numbers that are often really close to each other, and so a lot of sig figs go away when you do the subtraction, so it's good to have a lot of extra ones here. They didn't have equation for the area in the book. I mean, there actually might be one in the appendix. I'll take that back. But anyway, you could always just do it by taking the average of the two sides. If you remember for a trapezoid, just take the average of this distance and that distance and then multiply it by h, and you'll get the area like that. And we're going to need that when we go to put it in for this equation for Rn. That's the distance to the neutral axis, which, of course, remember, is different from the radius to the centroid, right? The centroid and the neutral axis are the same thing in a straight beam, but they're not in a curved beam. So we plug some values in, and I get 193.835. So the difference between these, we call that like an eccentricity. So I went ahead and subtracted the two out and have from each other. So here right there is the distance between them that we're going to need in our main equation. We also need to have the distance from the neutral axis to the outside fiber and the distance from the neutral axis to the inside fiber. And we're also going to need some loads, right? So we're going to need to know what the moment is applied there. So I made a free body diagram. Remember, you want to cut the thing right where we're looking for stress, so right there along that section. And the force is not aligned with the center of curvature, so I have RC plus RI. So we're going to take the moments about the centroid because the reaction force does act at the centroid, because that's like the central place where for an axial force, right? Sort of like the average location. So if you had one particular reaction, that's where it's going to be. So this is the location where we want to take the moments about, right here, so we can get rid of that. So if we take that force that we have on there, and these are kilonewtons and these are millimeters, so the kilo kills the milli, so we're fine with units. And I end up with some large 230,000 Newton meters. I also went just for the sake of completeness, went in and put in what that reaction is. So this one's going to cause an axial load, and this is going to cause a bending load. So we can go up to stresses, and here is the equation for going for the inside fiber, right? And so this is going to be tension, and this axial is also tension. So the difference between the outside and the inside is we use the CI here, and we use the RI here for the bending. So you see we have that area, the eccentricity, and RI, and we put it all together. So I had 21.36 from megapascals for the axial, and that's tension, with an additional 178.3 megapascals for a grand total of 199.7 in tension. Now for the other side, the outside, we're still in tension because of the force on there, but now the bending is going to cause compression on the outside. So I just went ahead and brought that number down. And really the differences between these two is, we use the CI here, the UCO, here's RI, here's RO, and we get a negative 93.41 megapascals. So the total is 72.05 megapascals in compression, and here are the answers. And because we can, I made an FEA model of these, right? So here is, I'm almost hesitate to even show this to you, but I don't have a high degree of confidence in the results for problem 1 because the loads were large enough that I had to turn on the large displacement solver, right? It's the nonlinear solver. And I also decided after my first attempt using solid elements, which didn't go off very well, because this is very thin wall right here, I decided to go ahead and use plate elements. So I'll show you what those look like right there. Here I'll show mesh. Yeah, show mesh. I think we'll do. Where's show mesh? There you go, show mesh. Okay, so I kind of meshed it sort of fine right there, but you could see that these are actually plate elements. I don't think SolidWorks' plate elements are very good compared to like maybe some ANSYS or Abacus or Nastran, other FEA codes. I put the loads right here onto this edge. Anyway, I solved it, and in the X direction show, right there you can see, so this is the X stress. If I go to this probe right here, and I go to that predetermined point right there, that's and oh, by the way, I put the solution loads onto this just to see if it caused that same stress, which it should, but this didn't, right? So this should really be like 41 KSI, and it's only got 33 KSI. But if you go to kind of points just a little to the side of it, it's got some that are kind of starting to get larger. So I almost wonder if the large deflection, maybe, I don't know. I just didn't, I don't really quite trust the results here. We also, if we go and look at the, this one should be more accurate. This is in the Z direction. I didn't have a very good plot scale there, but because it just looks green. But we can grab that point, and that's not good. No, why did you, what did I open up? Stress 1 in the Z direction. That's weird. Huh. Alright, I don't know why that happened. I don't want to get rid of that. Alright, that wasn't true a little while when I was looking at this previously. Let's try it again. It's got 0 KSI in the Z direction. I don't understand that. Did I accidentally change this? Edit definition. Normal stress in the Z. That should be the hoop stress. Well, I don't trust this thing at all now. Why to probe you? From the scale, it does look like it should be near 0 right there. But I got it. It came up to like 7 point something. No. Yeah. Yeah, something's messed up with this. I don't know. I don't know what it is. Alright, let's not even look at that one then. I'll have to troubleshoot it later. This did have a really large displacement, by the way, if you take a look at this right there. See? This is actually true scale. It's a scale 1 to 1. I think it would move like 2.5 inches, which is pretty large for this arrangement. Let me go to the other one. I'll have to troubleshoot that one. I don't know why it's giving me something weird. Ghost in the machine. Let's see, this is problem 2. Right? So this should be the right one, right? Problem 2, homework 4. Alright, so I made this, and here you go. I'm showing stress in the Y direction, so aligned with the Y direction. And you could see that, you know, I made the scale. Here's tension. Here, 0 is like right around where that light blue is, and then this is compression with that dark blue. So if we go and we probe, I'm just going to probe to these outside little edges right there, and right there. And you can see we get like 201 and 88 compared to what we were calculating before was what we calculated. Let's see, we said it was like 272. We're in the ballpark with the compression side was a little more off than the inside. We could also, if we wanted to, note that this is just to the outside corner right here. If I actually go through and look at the edge right here, let's take a look at this edge, and I'll just plot it. You can see that's true right over here in the corners, but it actually goes all the way up a lot higher here in the center. It's probably because the load is so large, right? So it's not like evenly distributed across the whole thing. This was not not unlike the other problems. It did not give me a large deflection warning. You can also see that, like, you know, this is it goes up a lot higher right to here. Well, actually not a lot higher. These are pretty close to the same, right? 88 all the way across, yeah. So it was sort of an interesting result that it gave me. This pretty significant distribution, so that outside edge was still got that guy. All right, I don't know what you're doing there. Right here, click him and update. All right, there you go. Yeah, you can see that that's a over 55 or like around 55 KSI difference between the outside and inside. So anyway, I thought it was quite interesting. I'll look into that a little bit more. But I got to troubleshoot the other one. I'm really disappointed. I wish I hadn't even shown it now. But I don't think people watch the end of these videos. I could do anything I want. I could like sing a song or something. But I think it's time to go home. I'm going home.